It's a cylinder. Specifically, it's going to be a cylinder kind of on its side. So kind of imagine spins around, and it is basically going to be a cylinder. We're going to use the idea of a cylinder to basically create the formula that we're going to be using to do these problems. Of course, we'll have like an integral and all that in it. We know that the basic formula for the volume of a cylinder, it's going to be the area of the base times the height. Like that's the formula you should know. That's the formula we have for all volumes of cylinders. For this one specifically, we can see the R value, again, is basically going through that region. So the R value would be 3. And the height of this one, since it's on its side, is going to be 2. So we can't imagine that this is just a cylinder when you trace it out. We can also rotate these regions in the other direction. So I took that same region. Let's revolve it around the y-axis. Revolving it around the y-axis, not any more exciting. Like it's still going to create just another cylinder. But this time it's kind of wrapping around this way to create that cylindrical shape. Volume is still going to be considered to be pi r squared. That's the area of the base times the height. So the volume, this one would be pi. This time the radius is 2, and the height is 3. And that radius is going through the region like this. And how can we convert this into like a calculus formula? How do we calculate, in calculus terms, what this is going to look like is we learned last week that volume we found by the integral of the area of a slice. And you could do that in terms of either dy or dx. Well, all these volumes that we do, they're going to be rotating. They all are going to have the same cross-section. What is the area of that cross-section going to be? They're all circular. So we have like this pi r squared action going on. And then we saw that the volume for the cylinder has the height in it. Well, for us, that height is going to be kind of translated to be in either terms of dx or dy. So it's literally the same formula that we did with volumes by cross-sections in many ways. We're just kind of generating the volume a little bit differently. For cross-sections, it's like you have the area and the volume being built on top of it. For revolutions, it's like you have a region and the volume is made by like spinning it around an axis to kind of trace it. Obviously, in calculus, we're not going to be finding the volumes of cylinders. They're going to look something more like this. You'll have a region defined by it. So I have y is equal to x squared minus 3x plus 4. It's also bounded by the vertical lines x equals 1 and x is equal to 3. And you'll also be told what you're revolving this region around. So this one, we're going to start off with like a pretty basic one. We're going to revolve it around the x-axis. So this region is basically kind of spinning around the x-axis, and that's going to trace out a 3-dimensional figure. Now, I don't always expect you to know like what this graph looks like or what this volume really looks like. I think it does help, but you can do it without kind of visualizing it in 3 dimensions. I did use a computer program to kind of show you what it looks like. I don't know how good of a drawing it is, but there is what this kind of shape looks like when you do trace it out. It kind of looks like, I don't know, like one of those chimney stacks from a nuclear power plant turned on its side. I don't know, something like that you can kind of imagine. It is a solid figure since we are rotating that kind of solid region around. Hard to tell in this, but you can see that like it still has circular cross sections going around. So we have this idea that there is this radius. Let me get a thicker marker. There is this kind of radius involved that is spinning around and tracing out this figure. So how do we find the volume of that figure? Like we basically need to think about volume as the integral of the area of a slice times dx or dy. So I'm going to work it out on this side just so I have both of them side by side. Don't overthink these problems. The way we determine whether it's going to be dx or dy is going to be the exact same way we determine dx or dy for area, and the exact same way we determine dx and dy for volume. How do I determine whether it's dx or dy is I want to draw like an example of like one sample radius. So how would I draw one sample radius? If I'm going around the x-axis, so I'm starting at the x-axis and then going out towards the edge of the region, and that's going to represent my radius. Since that radius is moving up and down, do you think we're going to do it in terms of dx or dy? Dx. So anytime we go up and down, we know that we're going to do it in terms of dx. Similar to cross sections where we had to identify an expression for the base, now we want to find an expression for the radius. Well, since we're going up and down, top minus bottom, so we're going to keep doing that again. So what is the top function? The top function was the quadratic minus the bottom function. What's the bottom function for this one? Technically the x-axis, which would be y is equal to 0. All volumes of revolutions have the same cross section. Since you're rotating it around, it's always going to be a circle. What's the area of a circle? The area of a circle is pi r squared. We already said we were doing this in terms of dx. What was r? R was this expression. So I plugged it in, and then we do need numbers on the integral sign. Well, if I'm in terms of x's, I need to have x values. This volume is starting at x is equal to 1 and ending at x is equal to 3. And that is our answer. Questions on that? Pretty straightforward. Mainly, if I just want to like summarize this, figure out if you're in terms of dx or dy, figure out an expression for r, and then plug it into, we know a circle is pi r squared, and then make sure you just stick an integral sign and a dx or dy in your answer. Try this one for me. I had this example 1a. If you finish it before I go over it, the next one is just us doing it around the other axis. But I have region capital R is enclosed by the graphs of y is equal to 2 root 9 minus x squared, and that is graph for you. Y equals 0, which is the x-axis, and x is equal to 0, which is the y-axis. So we can see that region in yellow. R is being revolved around the x-axis, so it's spinning around this direction. Write, but do not evaluate an expression for the volume of that figure. I think if you're trying to imagine what that figure looks like, I don't know, kind of like a sideways igloo or something, I don't know. Go ahead and try that one. And then we'll do it again, but just rotate it, or excuse me, revolve it around the y-axis. So again, I like drawing in a representative radius. When I draw my radius, I kind of always start at the axis you're rotating around and then go through the region. So that's going to be the radius that we're looking at. Are we doing this one in terms of dx or dy? Dx. So what is the volume? We know volume is equal to the integral of area. What's area? Pi r squared. And we already said we were doing this in terms of dx. If I'm doing it in terms of dx, I do want x values on my integral sign, so it's going to go from 0 to 3. And then what is the r value? Since we're doing it in terms of dx, it's going to be the top function minus the bottom function. The top function is that one, and that's a 9, minus the bottom one, which is 0. And you can definitely leave your answer like that. I will say often on the AP exam, they tell you to set it up. Sometimes if it's multiple choice, they might simplify it. Some ways that they often simplify the answer: pi is a constant, so it's often like just brought on the outside of the integral sign. And you'll see me write it that way often as well, just to kind of get it out of the way. But again, it's a constant, so it can go on the outside. Other things I can simplify, so like the minus 0 I could have left off. And I could square what's kind of inside that problem. So like 2 squared is 4, and that's a coefficient. The square root of 9 minus x squared is just 9 minus x squared. And of course, you can see if you simplify it, that does become a much easier integral to evaluate if you had to evaluate it by hand. Questions on that one? All right, do it again, but this time we're rotating it around the y-axis, so kind of a similar shape. Kind of looks like a Pope's hat or something. But try that one, right? Expression for the volume of that figure. And again, if you're doing it in terms of dy, then everything has to be in terms of y. So then checking your answer for this one, again, we're not going to make it harder than it needs to be. Anytime you're doing a volume of revolution, the cross sections are always circular. So we know that we integrate the area, it gives us a volume. The area of a circle is pi r squared. I stuck pi on the outside this time. You could have left it on the inside. Looking at my r, since I'm going around the y-axis, it's going to be going left and right. So we are in terms of dy. If I'm in terms of dy, I want everything to be in terms of dy. So it's going to go from 0 up to 6. And I do want to write an expression for r. Again, since r is kind of going left to right, we're going to do right minus left. And I have 9 minus 1/4 of y squared minus 0. I will say this, not that I want you to do this, but technically for these problems, if you flip around the right minus left and do left minus right, it wouldn't be marked incorrect. Since you're squaring it, it's going to end up being positive no matter what. Same thing if you accidentally flip over top minus the bottom. If you did bottom minus the top, it's not going to be marked incorrectly because as you're squaring it, it will always be positive. Now, if you're doing area, it would be wrong. But for one of these, it would not be wrong because of the square. Yes, Anna?
If you don't put minus 0 in that.
No, if you didn't put minus 0, that would be fine. Let's keep going. Again, these problems don't get too difficult, but try that one. So this is one where we're not rotating about an axis that's specific, like the x-axis or the y-axis, but we are rotating it about the line y is equal to 1. So we're spinning it around that line. So it's kind of like a solid funnel, if you will. But go ahead and set that one up, and I just have one more slide after this one where the graph is not provided. So we have this region S. It is bounded by the graph of f of x, which is that rational function you see in red, and then g of x, which is the line y is equal to 1. Don't need to worry about finding the intersection points because it does tell you that this region is starting at 2 and ending at 6. Again, they didn't give you those, and you would have to find those intersection points. So looking at this one, because the way we're rotating it is going to be in terms of dx or dy. Dx, so again, I start at the axis and then kind of go through the region. So r is going up and down, so I know we are going to be in terms of dx. Since I'm in terms of dx, I want the numbers in my integral sign to be x values. So we're starting at x is equal to 2 and ending at x is equal to 6. And then also, since we're in terms of dx, it's going to be top minus the bottom. So I have the top function minus the bottom function, which is 1, making sure I have all of that squared. So again, top minus the bottom squared, that is representing the r. This is representing the area of a slice, which we know is a circle, and of course the integral sign with the dx is what's making that a volume. Thankfully, that one we don't have to evaluate by hand. Questions on that one? All right, last slide. Try those two on your own. Should be able to figure out the region. Do, as you're graphing it, take note that I'm only focusing when x is greater than or equal to 1. Sketch the region, and then try numbers 1 and 2. Number 1, you're going to rotate the region described about the y-axis. And then part 2 is you're going to rotate that region about the line y is equal to 4. Just set these up. Don't worry about evaluating them. So we're looking at this one, you can kind of see the region I have shaded in pink. We have y equals x squared, but only when x is greater than 0, so we're kind of just in that first quadrant. And then y, which is equal to 4, which is a horizontal line. Graphing those, we do want to find the intersection point. Well, clearly they're intersecting when y is equal to 4. When y is 4, then x would be 2. So looking at these problems, I kind of did the one in orange is going to be that first question. If we're revolving it around the y-axis, so it's kind of forming like this solid bowl, if you will, and again, it is a solid figure. The radius would be going left to right, so we would want to do it in terms of dy. If you're doing it in terms of dy, it would go from 0 to 4, and then we do want to do right minus left. The right function in terms of y would be the square root of y, and then the left function would be 0, which you can leave off. Didn't ask you to evaluate this one, but this one will be pretty easy to actually evaluate by hand because you're really just finding the integral of y and then plugging in the top minus the bottom. Again, that pi could go before or after the integral sign since it's a constant. And then looking at number 2, we're going about the line y is equal to 4. So looking at the radius, it does go up and down. So it would be in terms of dx. If we're in terms of dx, the numbers need to be x values. And then we want to do top minus the bottom. What's the top function? The top function is y is equal to 4 minus the bottom function, which would be x squared. If you had to evaluate that one by hand, you would of course have to FOIL out the 4 minus the x squared. Questions on those two problems? All right, so looking ahead for kind of the rest of the week, just so you know kind of what's going on. Today I am going to officially assign homework 4. Tomorrow we're going to build on top of the disk method and do the washer method, which you can kind of figure out what that might mean. It's going to be figures that have like a hole in the center, so like fancy donuts. Wednesday is going to be a work day. Do notice I put this in Teams as well. I am changing homework number 6 to be optional because it is kind of redundant if you do homework 4 and 5 well. But again, I know many people want to do it for the extra practice and probably should do it for the extra practice. And then Thursday, we're going to be learning arc length, which will be a BC only topic, but it's actually how we find the length of a graph. Then you have the long weekend. Tuesday will be a review day, and then your test is going to be on Wednesday. Yes, with the modified Wednesdays, I know it's going to be kind of a shorter test, but I can kind of cover all this content in kind of a short number of questions. So that's kind of what you're looking at. If you work, you could probably finish most of homework number 4 in class today. So homework 4 is just 8 problems. And a calculator will be okay for numbers 24 and 28. If you should be able to finish homework 4 in class, in fact, I kind of recommend you at least finish it today so that tomorrow's notes of the disk and the washer method kind of mixed together goes a little bit more smoothly. But y'all can go ahead and get started on that. Again, if you work, you might be able to finish all of homework 4 in class before it ends. Do come, of course,